in the sky noise limited observation, such as the near infrared observation, the increased sky background emission level is causing that your exposure is actually getting saturated before you accumulate enough signal for your science target. So the question that the dilemma that actually you encounter in the typical near infrared observation is, how can you obtain high signal to noise data for your faint target in the flood of really bright sky background? One way to do it is actually just basically breaking your observation into the multiple, the smaller the exposure time, so that actually each exposure time is not saturated, but actually you accumulate enough, really the enough signal, so that actually eventually, by combining like a few hundred the fitch files, so that actually you can really achieve the desired signal to noise ratio. In such a case, each frame actually will be limited. I think they have the added contribution of the readout noise. Okay, and also that in that case you need to actually handle many hundred the fitch files per observation. That means actually in a single night of observation you are handling like thousands of fitch files, and that actually causes huge problem for the data storage issues and whatnot. So, and to mitigate the problems in the near infrared, also, they're actually utilizing the special capability of infrared array. Remember that actually infrared array allows the non-destructive readout, while that exposure to the science target is actually still the ongoing. You can actually read out intermediate result, right? So this, utilizing the non-destructive readout capability, there's the concept that actually comes in and then developed, that actually, without really writing out the information into the fitch file, inside in memory in array, the memories can actually contains this intermediate frame exposure data. Okay, so say that actually you are actually just creating, I think you want to actually just create accumulate the data from against the very bright sky noise, so that actually each individual exposure should be below the saturation limit, the level. That means actually that each per coadd frame exposure, that result is actually kept in the memory of the infrared array. Okay, while the exposure is actually continued. That means actually for the next set of coadd frame, that information can be added to the existing unsaturated the frame, the record. Okay, so that actually this concept of coadd, meaning that actually that adding the unsaturated images within the detector, the internal array, I think memory, is called the coadd. Then after a certain number of specified coadd, that actually the result can be written as the single fitch file. So in the coadded observation is actually specific in a way that actually because it interplay between the saturation level and the allowing that actually minimize the number of the detector read, I think the write out into the separate fitch file. Okay, so in the coadded observation, we need to actually think about several factors, such as how fast the sky is changing, and what sort of dither, and then coadd, and then how many repeat of these dither coadded observation that actually need to be chosen. So, and there are several parameters that actually we need to think about consider in the near infrared observation planning. So one is to subtract the dominant sky noise. That this is to subtract the sky effectively, we need to either use the dithering, okay, or if your science target is too large, so that actually the small fraction of the offset amplitude is not really effective, so that actually, for example, your main science target is extended galaxy that actually occupied 80% of the detector array field of view. That means actually you cannot actually really just do the on-chip small dither, meaning that actually if you do that, the median shift, they combine very actually the median out some of your source pixels, the fluxes in a special the pixels. In that case, the science target that actually being the extended source, typically they using the choose the nearby adjacent empty sky and taking the dither observation in that empty sky for the hope that actually just to create the master the sky noise frame. Okay? In that case, that actually the empty sky, the observation still need to be dithered because there can be actually the invisible but very faint, but the background, the sources that actually can still that actually contributing. Okay, and then you want to actually just kind of just the averaging that out by the dithering the observation. Okay? Then considering the saturation limit, you just decide how many coadd, meaning that actually you can actually just choose the coadd frame time, and the number of coadd. Okay? Then you need to actually think about the how fast that actually sky background is changing. So even for the good observing night at K-band, which is 2.2 micron, sky change in 20 minutes time scale. So meaning that actually if you the dedicated sky observation for your extended target observation was taken 30 minutes after the object time, then the sky the monitoring observation is useless. So that sky the monitoring either from the dithering or others need to be taken within the sky the variation time scale. The sky variation time scale at K band is 20 minutes. L band, which is 3.6 micron, which is lower end of the near infrared, the wavelength range, is the sky is changing in a matter of minute. Okay, and even at mid infrared, so if at mid infrared, sky is actually changing even in a matter of just fraction of a second. So in this mid infrared, we need to actually use the very specific mid infrared, the only specific observing technique, and which will be actually just shown and then discussed in the next lecture. Okay, then you need to actually choose the dither pattern in terms of dither amplitude and the positions, and finally that actually you need to decide when the how many times of repeat that all this coadd plus dither is necessary to achieve the final the desired signal to noise ratio of your science target. So let's just look at the more specific example. Okay, so in this the simulated the observation is actually happening at the K band. So meaning that actually the sky back the variation time scale is roughly about 20 minutes. So when you plan the observation, you need to actually make sure that the entire length of observation for the proper sky subtraction, that entire duration of the observation need to be actually within 20 minutes. Otherwise, you need to actually just default into the intermediate the sky the monitoring folded into your planning. Okay, so the K band observation is actually just the limit is 20 minutes. Okay, the sky variation, and you observe your target, which actually has the 2,000 count per second count rate. Okay, and then your source is actually spread over 4 pixels due to the point spread function structure of your telescope and an instrument. Okay, so the per second per pixel, the science target is actually contributing 500 count per second per pixel, right? Then some of the relevant information that you need to consider to planning the near infrared the observation is detect the saturation limit. What sometimes actually known as also the linear regime is 8,000 count per pixel. Okay? So you can, if you are the accumulated count from various source, from your science target or there's some noise counts or not, if it is actually going above the 8,000 count per pixel, then it is becoming saturated. Okay, so you need to actually make sure that the per pixel, the maximum count has to remain below the 8,000 count. Sky brightness at K-band is producing 1,000 count per second per pixel. Readout noise is actually 10 count per pixel per readout. Dark current is actually producing 100 count per second per pixel. Okay, and then your goal is actually you want to achieve the final signal to noise ratio of 100 data. How do you How do you actually plan out the near infrared observation? Okay? So this is the example. Okay, so the total the count per pixel per second for your science, I think for those 4 pixels occupied by your the science target is 500 count from your source, right? So remember that actually that 2,000 count was spread over 4 pixels. So per pixel, source count rate is 500, right? Then K-band brightness is contributing 1,000 count per pixel. So that actually the 1,000 from the sky. Then the dark current is actually 100. So per pixel per second at your source pixel is producing 1,600 counts per pixel per second. So meaning that actually that by mere 5 seconds of the exposure, these pixels actually becoming saturated. That's reaching the 8,000 count level. So meaning that actually that coadd frame time need to be actually kept at 5 seconds or lower, right? So that's the first number that actually obtained. So let's calculate the signal to noise ratio that actually from this 5 second frame time, the single coadd of the observation. So signal to noise ratio calculation. Signal is basically 5 second, okay, 5 second. The signal to noise ratio per pixel, right? So 5 second is for this 5 second is what that actually that the over the 5 second the per pixel that actually produce the 2,500 count per pixel, and that's the accumulated source, and the noise is actually for the 1,600 for the counting plus a noise plus the actually dark current, so that actually that the total noise is actually square root of 8,100. So that means actually for the 5 second frame time per pixel signal to noise ratio is 28. Okay, so to achieve that actually the desired signal to noise ratio of 100 per pixel, you need to actually increase the signal to noise ratio by 3.6 times. So to increase the signal to noise ratio by 3.6 times, the exposure time need to be increased by the square that actually the 3.6. So 3.6 to the second power is actually about 13 times. So that means actually that per pixel signal to noise ratio will reach 100 if you increase the effective total duration of exposure time by the 13. Okay, so imagine that actually now you are introducing the box 5 data observation. Okay, with each 5 second exposure per data position without using any coadd. Okay, so coadd is actually kept at 1 frame time is 5 seconds, but you are using the box 5 pattern, right? And then your signal to noise ratio from this box 5 object, the box 5 data pattern is becoming 28 times square root of 5. So that means actually there is the signal to noise ratio per pixel is 62. So to achieve the final signal to noise ratio greater than 100 per pixel, you repeat your data pattern 4 times or coadd 4 times at each data position. That means actually that your effective exposure time will be increased by 4 times. So that means signal to noise ratio per pixel will be increased by square root of 4, which is 2 times. That means actually that if you do either using the four coadd at each data position or repeat the whole data pattern for 4 times, then your signal to noise ratio per pixel at the end is 124. Okay, so this actually go above your desired level, right? And then let's think about the total duration of the observation. Okay, so that means actually that 4 coadd of 5 seconds at 5 data position. Just adding all this together is about 100 seconds. So that's about 1.5 minutes, which is actually well short of your final. I think the sky, the variation time scale of 20 minutes at K-band. So this is actually a good actually the observation setup. In that case, the signal to noise ratio of your source. So your final source, not signal to noise ratio per pixel. Your final source is actually that you actually just the integrating over all these 4 pixels, right? Over 4 pixels. So that means actually your final source, the signal to noise ratio is actually just 124 times square root of 4, which is actually in that case 248. Okay, that's the final signal to noise ratio. But that means actually this is a little too long. So that what I would actually do at the end for the choice is either using the repeating the data pattern for the 2 times, or the coadd per data position is actually only 2 with the frame time of 5. Then your final signal to noise ratio of the source will be 128. Okay. So in this case that actually that I'm actually just mixing the signal to noise ratio per pixel versus signal to noise ratio of your final the target, right? So imagine that actually that's a previous case that actually that all this the planning out was actually done with the per pixel level, and then your desired signal to noise ratio of 100 is per pixel, right? Then you can actually have an option, 2 different options. First option is 5 second frame time per coadd plus 4 coadd in each the data position using the box 5 data the setup, no repeat. Okay. Another way is actually using the single coadd and then coadd the frame time of 5 seconds, but using the box 5 data positions, but repeat the whole thing with the 4 times. Okay, so in either way, that actually from this you can actually achieve the final signal to noise ratio per pixel of 124. Okay, and then total duration is still there actually 100 seconds plus maybe that readout time and then telescope slew a few seconds, so that actually the overall duration of the observation is well within 2 minutes. So graphical representation of these 2 options are like this. In each box 5 position, okay, the coadd were actually just taken and just single box 5 pattern, or with just no the coadd. So coadd is actually kept at 1 with the 5 frame time is 5 seconds. You just basically just repeat the box 5 data patterns 4 times. Okay? That way that actually you can actually achieve the same the desired the result. Okay? Why do you actually really worry about this coadd? Because saturating the infrared array is actually really bad. So we need to actually just stay within the saturation limit of the infrared array at as best as we can, which is actually illustrated in the case. This is actually the one of the infrared array of the now that actually decommissioned the Spitzer infrared space telescope. So with the four is the four different the array. They're covering the different wavelengths region. So this is something like the 3.6 micron. This is 4.5 micron, and this is the about 6 micron, and then this is about 8 micron. Okay, and then you see that actually that you put a very bright the object on the array. Okay, not only that when you put the really bright object on the array, you can actually see that actually the so-called ghost images that actually that which will be explained in the next slide. The main problem is actually this bright source actually saturated the array very badly, and the charges actually the overflows the flowing the charges that actually produced by this saturating is actually they don't get that readout I think completely. So there is a trapped charge in that the badly saturated pixels. So meaning that actually when you take the different the observation by pointing the telescope into the different the region of the sky, you can still see that actually effect of the badly saturation, bad saturation from the earlier observation. And you can see also that actually causing that this saturation causes some pixel pattern noise in the shorter wavelength channel, and then you can actually see the remaining effect of the bad saturation from the earlier observation, which is actually called the latent images. And to remove these latent images, you need to actually wait for a long time, few hours, or you need to actually just reset the detector. Basically, just warm up the infrared array, so and then just heat up and then just remove all the trapped charges. So it is called the thermal annealing of the array. Then actually just recool, and then that actually the change the detector the behavior ever so slightly. So this is actually is undesired operation for this, especially the space telescope. So the saturating the infrared array is actually one of those really feared the operation in observation. That's why that actually we need to worry about all this the coadd, so that actually they remain below the saturation limit. And when you also they actually use really bright object in the sky, I think in the detector, that really bright object that actually that now that actually showing ever so faint that are previously unrecognized the image artifact. That because there actually there is multiple optical element in the telescope, the chain, that some light that actually just are reflected multiple times within the lens or prisms or dichroics and whatnot. So that actually that the multiple reflection they're causing some ghost images. Normally that actually this is invisible and then buried in the noise level. But when you're actually observing really bright object, these ghost images from the multiple interval the reflections were not actually becoming the apparent. Look at this ghost image and then ringing patterns or not. So not only that actually the saturation is really dreadful for the consequences of the infrared array by observing the really bright object beyond the level of saturation limit. Also that actually these ghost images oftentimes actually confusing and then affecting your your science operation. So also imagine that actually your main science target is actually like this guy. Then the avoiding this really bright object on the field is actually need to be planned in such a way that actually the pointing the telescope in such a way that actually the array is arranged in such a way that actually the bright source is off the detector. Okay? So in summarizing the near-infrared operation of the observation, okay, so non-uniform quantum efficiency need to be actually taken the out by flap fielding. High background level of the point source, you can actually use the small dither offset and then using the dithered observation. Extended target, you need to actually use the off-chip adjacent the dedicated sky observation. Non-linearity of the detector, you need to actually basically just stay within the linear regime and then under the saturation limit. Memory effect such as the latent the image, you have to actually stay and not to be stay within the unsaturated regime. Bad pixel, you can actually effectively the median out by using the shift and median. Cosmic rays also shift and median actually can effectively taken care of. The Darker current is usually taken out with this dedicated sky observation very well. Okay, and then hot rows, hot pixels, and the amplifier grows and whatnot. All these the detect a fixed pattern noise are actually nicely subtracted out from either the observation or the successive that dedicated sky observation and not. So this sums up the near infrared observations, okay, and then this is actually much more complicated than simple the optical observation, which is actually the oftentimes detect a readout noise limited observation, which is actually very simple. So as we go to the different wavelengths regime of the observational astronomy, there are actually that observing strategy is actually getting very complicated. Okay? So this sums up the near infrared of the observations in astronomy.